record. See if anyone else used this. Nobody used it? Okay. Because I'm curious how people dealt with the issue of if we go to our tests and we run our tests, one issue that you potentially ran into, and I don't know because you all got past your tests. Oh, first of all, some of you did not do this. Well, no, almost all of you did it. But if you run, you should run all of your tests, not a single test, right? You can run individual tests and it will pass and give you this one nice little test here. But this contains key null test. And so if I go, how do I figure out why I'm not passing that test? So let's just talk about running through test cases. How did you guys do it when you were figuring out that you didn't pass a test? Yeah, let's go to the test, right? So if I go down to contains key null test somewhere in here, there we go. So what does this do? It creates a new map. It puts in high and null as the value, and then asserts true that it contains key high. So what is the expected specification of your code here? It's expected. Well, not what do you mean true? There's no Boolean in here.
Assert that it contains key method returns true.
If what?
If there's high in the key.
And more importantly,
And there's a value.
well, what is this testing?
The key is null.
No, the key is high. The key is there.
Value.
The value is null. What it's testing is, hey, we put in a key, but we said the value is null. And could we design code where that wasn't the case? Sure, we could. We could say, hey, if you don't put a value in here, that's not a valid key value pair. It's a null, right? But what is this telling us? That in this code, you can have a null value. So if I go look at my code, I'm like, okay, my contains key. I got to go check that out. So I'm going to go find my contains key in my code. And then I'm going to say, here we go. I put in here that if key equals null, I'm going to throw an illegal argument exception. And then I return get key does not equal null. Can I do that? Why not? Because it can be null. We just looked at that thing, and this thing, my tests are saying that whoever designed my test cases is saying, hey, no, this can be null. So I can't use my get method to get my contains key. And this was one simple way to use contains key, right? I can use one of my other methods to figure out if it contains the key. I can just do this get method. So how did people do their contains key so that we had that possible null issue? Or got around that null issue? How do people construct that? And if I go look, I was like, oh, I wonder what the Princeton review did, or Princeton class did. Well, guess what? Contains key. Where did I go here? We got here is empty size contains. If key equals null, throw if get key does not equal null. So what does their code do? Null is not valid in the Princeton version of this thing. Okay, so we're seeing differences in just the overall construction of this thing and how people build it. Princeton says, no, we're not going to take nulls as values. This is much easier to deal with. But our test cases say we want to be able to handle that. Logan, what were you going to say?
Oh, we're just going to say like, just do like if and no is no return false.
Well, then how are you getting? And then what are you doing for contains? Because I can't do that in my method. My method says if return key does not equal null. That's my whole method here. So how are you figuring out if it contains?
Well, I did.
That does what?
Looks at the root and the key, and then basically, like if that node is no returns false.
One more time?
Like.
Here, do you want to go ahead and share it?
Yeah.
Okay. Okay, so it was this back talking in the background. Jeez. Yeah, okay, I won't even go there. Okay, yep. Temp compare to. Okay, talk us through it.
So, basically, it like looks through this helper, then, um, I did like this attempt to like check, like, the key, like, and then, this goes to the left side, this, right side.
Okay.
And then basically, once it's like found, you just, it keeps on going until it's found. And then it basically like returns true, so like, so it was like, basically on, like if we're looking for like C or something like that,
Mm-hmm.
we kind of go like, they go like zigzag down, right in front of down, and then like, yeah, and then if we were looking for like, let's say we're looking for like I, then it would go like, it would like go to like the right.
Okay. And you tested it and it works other than just the test cases?
Uh,
Okay. All right, so you just did the similar recursive version to essentially what your get would be or anything else, yeah?
yeah.
Okay. Other folks, what do other folks do? Mary, you want to share? What's that? It's similar? Okay. Want to share it? Figure out how to turn that off. All right, so but you flip it on its head a little bit. You return true if we check if it's equal first, and then go through and just go through right and left. If key equals null, if key, cool. But
Yeah.
same idea. All right, anyone do anything different? Radically different, Donald, do anything radically different? Similar idea? Okay, Ethan? Same thing. Okay, cool. There is a sort of another way to do this, but I'll show it to you and then you can tell me what we need to have for it to work, which makes your life a little bit easier, potentially. And we're not quite there yet, but it's this. We have to use generic for K in this. If K equals key, return true, otherwise return false.
Oh, right, because it's iterable.
Well, is it iterable? As we have it, as you all have it constructed right now, is it iterable? It's not, right? So, but you can see where being iterable is super helpful, right? Because could I do this with a for loop?
Oh, but you need to do it that way, checking if it's larger or smaller.
Yeah, I could potentially do it with a, well, what would my condition on my while loop be?
Well, the node doesn't, wait a minute. while left and right is not null.
So while, or while left or right is not null. Yeah, it kind of gets messy, right? You can kind of think through like, oh, that gets messy. What do I not have to do it with a for loop? What do I don't think I have. Oh, I do have. But we don't actually, I don't think we use it anywhere, right? Which is size. Would size be helpful? If I was trying to use a for loop? Would it be necessary if I'm going to use a for loop? How could I do it without use a for loop without size? I'm open to ideas. I can't think of one, but
As long as it's not null, you just you like you write it goes next on next.
there's no next. It's a binary search tree, so we have to like go. Yeah, so I guess we'd have to while for. Yeah, it gets ugly, right? This is where we can see where iteration and a for each loop becomes super handy. Okay, hopefully you can see that. Okay, cool. Any other questions on that? So what we're gonna do is you're gonna go to the home page, and we're going to transcribe sort of back and forth a little bit. But if you click on the very bottom, you'll see this leak code BST. And if you click on the leak code BST, it takes you to hopefully, oops, did I put in the wrong place?
No, it took me to like introduction to BST.
Define, there we go, introduction to BST, good. The definition of a binary search tree. What defines a binary search tree? Because some people actually screwed this up on the quiz. What are our definitions of a binary search tree? On the home page, right at the bottom, right there.
Each node cannot have more than 2 children.
So each node can only have 0, 1, or 2 children. What else?
Left must be less than the parent node.
Yep.
And right must be greater than.
That's it. That's our binary search tree definition. Mary, you good?
Yeah.
All set? Okay. So those are our 2 pieces of binary search tree, right? We can have 1, 0, 1, or 2 children, and everything on the left has to be smaller than me. Everything on the right has to be bigger than me. Okay. And this just walks through, this is sort of everything we've already talked to about. But what I want you to do is skip down to basic operations and click to search in a binary search tree. And have at it. We're going to go through some of these leak codes. And part of the thing behind leak codes for me is 1, they're just great practice. 2 is these really are, like if you have any desire to go forward in computer science, either in college or go find a job, these are the types of questions you'll run into. And so when you go up and you say, hey, I have already solved, I don't know, 50 leak codes in high school, people will be impressed. And then apparently you have to hit like 1,000 to make it really impressive or something like that. No. Probably not that many, but they do say that if you go in, like if you're actually into that particular thing, if you really want to bang out leak codes, the first 50 leak code problems are the ones, these right here. And we've already solved some of these, but these are the ones to tackle. So there you go, your work cut out for you. But for right now, we're going to stick with this search in a binary search tree, BST. So if you go there, it sort of talks about what we're doing. Hopefully you've already figured that piece out. And then you're just going to implement this. And I'm happy to have you copy and paste your code from what you already have into here. But you're going to see we have search, insertion, and then we get to play around with deletion, which we don't have yet. But this is where we're going to try to get our deletion to work. And then we can copy port that from leak code into our IntelliJ. And I'm curious to see what you all think about the way they talk through this and introduce it, if it's useful, if it's not, right? So these first couple of pieces are just walking through and looking for you to solve it. And our search hopefully is quite simple. They already give us like the whole structure of the tree. Down here, right? They're giving us this. And this is again the type of thing you'd see if you were given an interview problem. You'd be like, they'd give like, okay, this is what you've got to work with. Have at it. This is all you've got to work with. You don't have any other methods, right? You've got your nodes, your right and your left, and your constructor for your tree node with a value and a right and left node. Have you already done all these?
I think so, last year I did. What do you think about this program?
Where are we?
Yes,
What do you want to get into?
well, it's artificial intelligence plus like business.
Yeah.
But at the same time, if I do this major, I can't major in the side.
Oh,
Because they said that, well, the requirement was like, the degree cannot combine with an additional majoring as with business and wellness engineering.
but I'm assuming, click on your curriculum for a minute. I'm assuming, let's see, core requirements, financial account, managerial.
That's the business part.
Yeah.
And that's the concept part, but there's gonna be,
Programming, data structure, discrete. I mean, honestly, those first 5 classes you've essentially already covered. So it's. So the AI is 1, 2, 4, what's the integrator? I mean, it really depends, how much business you want to do. Do they have, I'm assuming you can take all those AI courses through another outside.
I guess,
Major.
yeah.
My 2 cents on it would be if you go that route, you are sort of limiting yourself a little bit more to business as opposed to comp sci in other areas. Whereas if you just want to comp sci, you could take all those classes
Yeah.
and have a comp sci degree as opposed to an AI for business degree.
Right.
I mean, it looks like a cool program, so I don't think you can go wrong either way. So it just depends on how interested in business you are. And if you're like, that's what I want to do, then that's great.
Or I can just like go CS and like a double major in like business or econ.
Get a minor in business. Honestly, I think if you come out with those skills in general, if you like, you know AI, you're gonna be just fine. Doesn't matter what your other courses are. But if you can pepper in business courses or whatever, you know, and the other thing is that it just gives you more options as you're there. If you decide to be like, oh no, my focus to be more CS in medicine or bio, you know, whatever it is, you have that chance to go other directions. Whereas with this, you're kind of like, okay, this is my route, at least through college. And then you can change your mind later on. But it does look like a cool program, so. Yeah.
So like, right now, if you study, let's say algorithms and stuff, what are like the jobs in that?
Algorithms?
Yeah, because like, surely the job isn't to solve that algorithm problem, right?
Yeah. I mean, so much of it right now is AI. So it's AI algorithms. But then if you're like, hey, no, I'm really into like other path valuing algorithms or stuff like that, there's definitely jobs in math, like working on mapping programs or stuff like that with graph algorithms. And then just straight theoretical work. If you want to get a PhD, then you get theoretical, you know, algorithm work. But that's like if you're really just like, because algorithms are cool. So, you know, that's one way to go about it. But that again, sort of limiting, especially right now. I mean, so like everything right now is AI, like it's all the jobs, all the interest right now is in AI and AI algorithms.
Yeah.
Beyond that, it's there's not a whole lot out there. I shouldn't say that because there's still, I mean, software development is still like just straight software development is still way more in need than anything else, despite all the claims of more software development jobs. Photography,
Yeah.
huge one with algorithms, depending what you get into. And super interesting as well. Data engineers, so not data science, but data engineers, we do a fair amount of graph algorithms, stuff like that. So that's one of them.
But not as much as AI.
Not right now, no. No, AI is the in-demand skill right now. Oh, sure. Try and run it. Just make sure you cover your theoretical bases. Just use your code from your binary search tree. They don't actually do that, right? So you should just go, here's your code from your binary search tree. And from IntelliJ. And work it out from there.
I have my last year's answer.
I'll do insertion too. I'll do search and insertion. I mean, you can go straight to there, but it's up to you. Did you get,
Yes.
we did that, we didn't do insertion last year?
Um,
Well, you should do insertion and deletion.
oh wait, it's locked.
It's locked.
Uh,
It should be, because I don't pay for anything, I just logged in, you might have to log in. But you shouldn't have to pay for anything. So do like, be careful with your. So Mary, like think about with your comparisons. In this tree node, what do we know? We gotta. Well, I don't want to give it away, but. Is this a map? Do we have key value pairs here? Does it matter? No, because map and a set are the same thing, right? So what do we know about the values inside the nodes? What's given about the values inside the nodes with this thing? What type of thing are they?
Integers.
They're integers. So you can just treat everything as an integer. Yep. You know it's all integers, right? So this actually simplifies our binary tree because we know for a fact that they're all integers. You should null check your root.
how to return like the subtree and it's 213, so it's BFS, right?
For which one? Sorry, which one are you doing?
Like the search one.
You
First one.
it does it matter? Oops.
Well, the first test case is 213 instead of like 123. So for the first test case.
Find the node. That's the node's value, return the subtree. Ba, 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 bum. Yeah, but you just need to think about what you're returning mostly. You don't actually have to be that concerned about the piece. So this is actually there's one trick to this thing that some of you might be running into, right? If we look at this thing, it's a little bit different because it's not saying, what is it not doing? We're not return. What are we returning?
The tree node.
Yeah, but if we think about, so we've given the root, integer val find the node in the BST that the node's value equals val and return the subtree rooted with that node. Right? So in this case, we've got this tree, 4, 2, 7, 1, 3. We're looking for 2, but we're not returning 2, we're returning that whole subtree. Okay? Yeah.
Well, I just returned the tree node and import.
Yeah.
Oh, is that how you return?
Yeah. So but if I'm returning this tree, like if I'm returning 2, 1, 3, what do I return?
Oh,
2. If you return 2, you're returning the whole subtree. Because it's the root of the rest of the tree. That's the beauty of recursion. Again, if you get that to work, go on to insertion. This part talks about it. The second part makes you do it. And then if you nail that, we'll take a crack at deletion. So we're missing, why are we missing so many people today? Stross, Sienna, Daniel.
That's a touch at the bottom, yeah, that's not. Oh, it's, I. Thought it was. Couldn't understand why it's.
All right, do you understand why it's right?
No, so that's what we're doing.
Huh?
So that's what I'm still looking at it.
What part's confusing?
I think just this condition. Well,
Then pull it out, put it somewhere else. If it doesn't make sense, pull it out.
yeah, but,
So you gotta put it somewhere else. But please think through the rest of your code, right?
yeah.
I was trying to do this assignment, I was like. I realized I was doing this.
Yeah.
It was kind of confused.
Okay.
One thing, we have a constructor in the insert problem, so how do we like create a new tree node?
Yeah, you got instructors there. Those lines, 8 and 9 are instructors.
But it's not letting me create a new tree node.
Scroll up. Yeah, because you have, you have to pass in 2 or right, you have, look at your instructors. You can either pass in a value or a value and a left and right node.
Oh,
You just have to make sure your parameters are correct.
that was different from my
Yeah.
IntelliJ.
Yeah, so again, it's a little bit different than our intelligent ones for sure.
Yes.
You figure it out?
Yeah.
Okay. So we could theoretically, right? So we're gonna check real quickly. Everyone's got search, right? Right, we could theoretically combine these two things. Why? The first two if statements.
That's their return, their root anyways.
They're both returning the root, right? So if the root is null, we're returning null. Well, that's the root. And if we found the value, we're returning the root. So theoretically, we can just combine those. We want to be a little bit more efficient. Otherwise, we're going to search left, search right, or search right, left, right? I assume I could probably also, yeah, no. So that's that. And then just be careful with your constructors in your insert. But again, you should be able to grab your code from IntelliJ. And we don't have insert, we have put. So can I actually do it like whole hog here? Oh, no, we can't. Oops, we can't do that. Okay, I didn't lie, I fibbed. It's not easier to import your code from your binary search tree. You can use the same concept, but don't try and import it because we're not doing a map, we're doing a set, so different. How are we doing?
Like, were we supposed to do the blockchain already?
You should make sure you have your insertion and then start working on deletion, yep. So once you've got insertion. Then you wanna work on deletion, yep.
Have like, some sort of incompatible type. You want to. Oh, does a method need to return something?
Yeah, so that's, so you're, well, no, you wanna make your private method also void. You wanna match,
Oh, the original question was like,
so that's, yeah, no, you gotta, don't change the, you gotta make sure you don't do that piece, so. It's tree node. You are returning a tree node, so put it back to tree node. Public tree node, insert into BST. Tree node root int value.
Oh,
Um,
then I need to change this logic.
so then you just need to return a tree node.
Oh, I see.
Recode now is a visualizer in there?
It's not working anymore. Let's do that. And let's see, insert. It's the last one.
What's up?
Like a low constant.
For which one? For insert?
Yeah.
No.
Oh, you just have to, insert that.
Yeah.
Are folks becoming more comfortable with the recursive calls on these things? Slightly, is that what you said?
No,
That's fair.
considerably.
Oh, no, I think, Ethan, did you say slightly?
Yeah.
Yeah, that's fair.
It's, I think it's easier now for me to kind of fly out.
Yeah,
I mean, like the BST version is not that hard to conceptualize.
I feel like binary search tree is nice because it is the probably, at least for many people, it's the easiest recursion to think about because it really lends itself to recursion.
Yeah.
It still can be really tricky to sort of wrap your head around. That being said, I do think it is the easiest recursion because you're just calling them in that way.
Probably easier when you have like the visualization. Because then you feel like a visual in there.
Mm-hmm. Through the visualizer on IntelliJ. Yep, definitely. All right, so let me just be clear on this. So on Wednesday, SATs are on Wednesday, right? Okay, and so we will have SAT. Okay. In class, oops, let's